For chapter 15, we'll be talking about thermodynamics. And this topic here is one of those big topics if you end up pursuing physics or actually even any other science. Um, Thermodynamics is kind of pulls together everything we've been discussing over the last few chapters. So as you can see, we'll go over a few laws. The first law of thermodynamics, heat engines and their efficiency. The second law of thermodynamics restated, applications of it. You'll see these examples pretty much in everyday examples. We'll go over entropy and the statistical interpretation of entropy as well. So this chapter is going to be very important for you to go over. So let's go ahead and get started. So for figure 15.1, a steam engine uses heat transfer to do work. Tourists regularly ride this narrow gauge steam engine train near the San Juan Skyway in Durango, Colorado, part of the National Scenic Byways program. So steam engine is a prime example of heat transfer and thermodynamics. We know that some type of fuel in here, whether it be coal or something else, is being burned, giving energy to the rest of the train, to the engine, and therefore you see the steam coming out of here from the residue that's being produced by the fuel. Like I said, it could be any type of material being burned, used, anything can be burned really. So the first law of thermodynamics applies the conservation of energy principle to systems where heat transfer and doing work are the methods of transferring energy into and out of the system. The first law of thermodynamics states that the change in internal energy of a system equals the net heat transfer into the system minus the net work done by the system. So in equation form, you have this where U is the internal energy. So this delta U gives you the change in internal energy of the system. Q, again, is the net heat transferred into the system. We've been dealing with Q for the last few chapters, and we know about work. Work is the net work done by the system. That is, W is the sum of all work done on or by the system. We use the following sign conventions. If Q is positive, then there is a net heat transfer into the system. If W is positive, then the work in the net work done by the system. So positive Q adds energy to the system, and positive W takes energy from the system. Thus, delta U equals Q minus W. Note that if more heat transfer into the system occurs than work done, the difference is stored as internal energy. Heat engines are a good example of this. Heat transfer into them takes place so that they can do work. We will now examine Q, W, and delta U further. So we have this system here where we're putting Q is going into the system and work is being taken out by the system. So the first law of thermodynamics is the conservation of energy principle stated for a system where heat and work are the methods of transferring energy for a system in thermal equilibrium. Q represents the net heat transfer. It is the sum of all heat transfers into and out of the system. Q is positive for heat transfer into the system. W is the total work done on and by the system. W is positive when more work is done by the system than on it. The change in internal energy of the system, delta U, is related to heat and work done by the first law of thermodynamics. So Q in minus your Q out will be your total Q, and work out minus your work in is your total W. That is the work done out of the system minus the work done in the system will give you your total U. And same thing for your heat transfer Q. Heat transfer, a less organized process, is driven by temperature differences. Work, a quite organized process, involves a macroscopic force exerted through a distance. Nevertheless, heat and work can produce identical results. For example, both can cause a temperature increase. Heat transfer into a system, such as when the sun warms the air in a bicycle tire, can increase its temperature, and so can the work done on the system, as when the bicyclist pumps air into the tire. Once the temperature increase has occurred, it is impossible to tell whether it was caused by heat transfer or by doing the work. This uncertainty is an important point. Heat transfer and work are both energy in transit. Neither is stored as such in the system. However, both can change the internal energy of a system. Internal energy is a form of energy completely different from either heat or work. So we can think about the internal energy of a system in two different but consistent ways. The first is an atomic and molecular view, which examines the system on the atomic and molecular scale. The internal energy U of a system is the sum of the kinetic and potential energies of its atoms and molecules. Recalls that kinetic plus potential energy is called mechanical energy. Thus, internal energy is the sum of atomic and molecular mechanical energy. Because it is impossible to keep track of all individual atoms and molecules, we must deal with averages and distributions. A second way to view the internal energy of a system is in terms of its macroscopic characteristics, which are very similar to atomic and molecular average values. Macroscopically, we define the change in internal energy, delta U, to be that given by the first law of thermodynamics. Many detailed experiments have verified that delta U equals Q minus W, where delta U is the change of total kinetic and potential energy of all atoms and molecules in a system. It has also been determined experimentally that the internal energy U of a system depends only on the state of the system and not how it reached that state. So just that moment in time. More specifically, U is found to be a function of few macroscopic quantities, pressure, volume, and temperature, for example, independent of past history such as whether there has been a heat transfer or work done. This independence means that if we know the state of a system, we can calculate the changes in its internal energy from a few macroscopic variables. So we know from previous chapters that pressure, volume, and temperature are all kind of related, and you'll see how in a minute. So for example, 15.1, we have suppose there is a heat transfer of 40 joules to a system while the system does 10 joules of work. Later, there is a heat transfer of 25 joules out of the system with 4 joules of work is done on the system. What is the net change in its internal energy of the system? Okay, so we have Q. We need to use is delta U minus Q, or equals Q minus W, right? So first we have to find our Q. Remember, it's the Q in minus the Q out. So that is the rule we're following. So suppose we have 40 joules to a system first. So we have 40 minus 25. The 25 is out of the system. So we do 40 minus 25, that gives us 15 joules. Similarly, the total work is the work done by a system minus the work done on the system. We have, while the system does 10 joules, so that's work done by a system. And then out of the system is 4 joules. Is done, while 4 joules is done on the system. So we do 10 minus 4, that gives us 6 joules. So thus, the change in the internal energy is given by the first rule. So we do Q minus W, so we do 15 minus 6, and that gives us 9. So we can also do this with a few extra steps. So first, we consider 40 joules transferring 10 joules of work done. So we can do this all together or piece by piece. This part here was all together. This is piece by piece. So for the first part, we have Q1 minus W1. So we do the 40 that was done right here to a system, because that was Q1, minus 10, which was the work done. So that gives us 30 joules. Same thing with the second part. The only difference here is that we have to be careful because here 25 joules of heat transfer is transferred out. So we know that there has to be a negative there. And same thing for the 4. That is work done on the system. So there has to be another negative there. So that gives us negative 21. we put these two together, we get 9 joules of change in internal energy. So both ways work. The difference is here is that this is a bit longer stepwise, and you have to be careful with these negatives. If these negatives aren't there, you'd have 25 minus 4. Well, that gives you 21. But then when you're putting it all together, you're going to have 30 plus 21. You're going to have 51 joules, which is not the correct answer. So for B, what is the change in internal energy of a system when a total of 150 joules of heat transfers occurs out of, so from the system, and 159 joules of work is done on the system? So we use that same equation, but here we have to be careful with the wording because the net here the net heat transfer and total work are given directly by Q is going to be negative 150 and your W is going to be negative 159. So here 150 occurs out of the system. So if we look back over here, if it's out, there's your negative right there. And 159 of the work is done on the system. If you go back over here, this gives you a negative here inside the system, the work done in the system. And you can see the illustrations down here as well. So we use the same equation, just got to be careful with the negatives, and we end up getting 9 joules here. So this is just another breakdown of the first law of thermodynamics, your internal energy, the sum of kinetic and potential energies of a system's atoms and molecules. Can be divided into many subcategories, such as thermal and kinetic energy. Depends only on the state of a system, such as your pressure, volume, and temperature, not on how the energy entered in the system. Change in internal energy is path dependent, so it doesn't matter if the state changes. Your heat, energy transferred because of a temperature difference, characterized by random molecular motion, highly dependent on the path. Q entering a system is positive. For work, energy transferred by a force moving through a distance, an organized, orderly process, path dependent, work done by a system either against an external force or increase in volume of the system is positive. So here are some examples for that. For the human metabolism is a conversion of food into heat transfer, work, and stored fat. Metabolism is an interesting example of the first law of thermodynamics in action. We now take a look on these topics via the first law of thermodynamics. Considering the body as a system of interest, we can use the first law to examine heat transfer, doing work, and internal energy in activities ranging from sleep to heavy exercise. What are some of the major characteristics of heat transfer, doing work, and energy in a body? For one, body temperature is normally kept constant by heat transfer to its surroundings. This means Q is negative. Another fact is that the body usually does work on the outside world. This means W is positive. In such situations, then, the body loses internal energy since delta U is Q minus W, all of it is negative. Now consider the effects of eating. Eating increases the internal energy of the body by adding chemical potential energy. This is an unromantic view of a good burger. The body metabolizes all the food we consume. Basically, metabolism is an oxidation process in which the chemical potential energy of food is released. This implies that food input is the form of work. Food energy is reported in a special unit known as calorie, and we've gone over that in the last chapter. This energy is measured by burning food in a calorie meter, which is how the units are determined. Human metabolism is a conversion of food into heat transfer, work, and stored fat. Metabolism is an interesting example of the first law of thermodynamics. I think this is just a breakdown of the same one. So for figure 15.5, we have A, the first law of thermodynamics applied to metabolism. Heat transferred out of the body Q and work done by the body W remove internal energy, while food intake replaces it. Food intake may be considered as work done on the body. So for B, Plants convert part of the radiant heat transfer in sunlight to stored chemical energy, a process called photosynthesis. So heat coming in and heat going out. And here we see the total internal energy. You have Q going out, but the work being out of the body makes it positive. So you pretty much have a negative Q minus W, because W should still be positive, but we replenish our internal energy with the food energy. So, schematic representation of a heat engine governed, of course, by the first law of thermodynamics. A heat engine is a system that allows us to use heat transfer in order to do work. A closed system means that no mass leaves or enters the system. An open system allows mass to move freely in and out of the system. An isolated system is a closed system in which heat can also not enter or leave the body or the system. An isolated system is an idealized setup, but it is impossible in real life. It is impossible to devise a system where Q out equals 0, that is, in which no heat transfers occur to the environment. It is physically impossible to have a perfect engine. That's what that would be called. So for figure 15.8, you have heat transfer to the gas in a cylinder increases the internal energy of the gas, creating a higher pressure of the temperature. So here we have heat coming in. You have your force equals your pressure times your area, and your delta U is just going to be your Q in. For B, the force exerted on a movable cylinder does work as the gas expands. Gas pressure and temperature decrease when it expands, indicating that the gas's internal energy has been decreased by doing work. So here we have a distance here where the cylinder moves, so we have our distance for work. We know a force is being pushed back on it, and the work done is going to be in this rotational motion, where work out is going to be F times D. So here is our internal energy here. So for C, heat transfer to the environment further reduces pressure in the gas so that the piston can be moved more easily, returned to its starting position. So here basically the piston is going in a circular motion this way. And so here your work in is going to be your force after the motion times the distance. The new distance is from here to here, and that'll give you your Q out. So each of these steps you can find your internal energy, and if you wanted to, you can find the total internal energy of the whole system after the movement. So here for 15.9, an isobaric expansion of a gas requires heat transfer to keep the pressure constant. Since pressure is constant, the work done is P times the change in volume. So here we have our work out, which means the work done here is FD. We have our distance here. But we also know that it equals PA, that our force is going to be PA. So our total work out is going to be pressure times your change in volume. And this is one of those equations we went over in the last few chapters. And of course, you have your heat coming in. So this is your heat in, and this is your work out. So both of these would be positive in this case. So for figure 15.10, you have a graph of pressure versus volume for a constant pressure or isobaric process such as the one shown in 15.9. The area under the curve equals the work done by the gas, since W equals P delta V. So here you have our pressure in the y-axis, V in the x-axis, and the area under the curve here would be your work. There's a way you can do this in using calculus, but that is for university physics. So figure 15.11, you have for A, a more general PV diagram in which pressure varies as well as volume. So the work done for each interval is its average pressure times the change in volume, or the area under the curve over that interval. Thus, the total area under the curve equals the total work done. So same representation, except here there's actually a curve. For B, work must be done on the system to follow the reverse path. This is interpreted as the negative area under the curve. So for here, the path is this in this direction. So our W in equals our negative W out. So PV diagrams clearly illustrate that the work done depends on the path taken and not just on the endpoints as seen in the next figure. So for here, 1512, for A, the work done is going from A to C, depends on the path. The work is greater for the path ABC than the path ADC. So A, B, C, then ADC. In both cases, the work done is the area under the path. This area is greater for ABC. So for ABC, you're talking about the whole area here. For ADC, you're talking about just this part down here. So you can see that the curve is obviously greater for ABC. So for B, we have the total work done in a cyclical process ABCDA. So we're going A, B, C, D, A is the area inside the loop, since the negative area below CD subtracts out, leaving the area inside the rectangle. The values given for the pressures and the change in volume are intended for use in the example below. So we go from B to C. So this is the area inside the loop. The area inside any closed loop is the work done in a cyclical process. If the loop is transversed in a clockwise direction, work is positive. It is work done on the outside environment. If the loop is traveled in a counterclockwise direction, work is negative. It is the work that is done to a system. So here, a clockwise direction is positive. This would be a positive work. So for this example, we have calculate the total work done in a cyclical process A, B, C, D, A, shown in the figure by the following two methods to clarify that work equals the area inside the closed loop for a PV diagram. Take the data in the figure to be precise to three significant figures. So first, we got to calculate the work done along each segment of the path and add these values to get the total work. So for A, we have work done between A and B. We know that is the pressure of A and B times the change in B between A and B. So pressure A and B is right here. We have 1.5 times 10 to the 6. And the change in volume between A and B is 500 centimeters cubed. So we just plug in directly to this equation. We have 750 joules. So for B and C, we know that the volume change is 0, right? So the overall work done is 0 for that one. So for CD, we have C here to D. Our pressure given is 2 times 10 to the 5th. But now here we're going in the reverse direction. So we know that our change in volume is going to be negative, which is why there's a negative right here. So that'll give us negative 100 joules. And same thing here. From D to A, there's no change in volume. So work done on D to A is 0. So once we add all these up, you have work done on A and B, 750, which we found. B and C is 0. C and D is negative 100. And D and A is 0. So our total work done is 650 joules. So now we have to calculate the area inside the rectangle ABCDA. So if we do that, we need to have our total pressure times our change in volume. So our total pressure would be pressure A minus B, or pressure AB minus pressure CD. And if we put that all together, we see that we still get 650 joules. Okay, so both methods work. So for A here, the upper curve is an isothermal process. That means that your change in temperature is 0. Whereas the lower curve is an adiabatic process. That means the change in heat is 0, or heat equals 0. Both start from the same point A, But the isothermal process does more work than the adiabatic because heat transfer into a gas takes place to keep its temperature constant. This keeps the pressure higher all along the isothermal path than along the adiabatic path, producing more work. The adiabatic path thus ends up with the lower pressure and the temperature at point C, even though the final volume is the same as the isothermal process. So for B, the cycle ABCA produces the net work put. So we have A, B, C. This would be the network. And if we were to do that for A and C, and let's call this point D, we would get the work done there. So for isobaric, that just means your work is P times delta V, and that means constant pressure. For isochoric, constant volume, work done is 0. So these points right here would be that, B and C would be that, A and D would be that. Isothermal, constant temperature, Q, our heat, is equal to our work. And adiabatic means no heat transfer, so our heat equals 0. So reversible and irreversible processes. A reversible process is one in which both the system and its environment can return to exactly the states they were in by following the reverse path. An irreversible process is one that depends on the path. If the process can go in only one direction, then the reverse path differs fundamentally and the process cannot be reversible. Real microscopic processes are never exactly reversible. If there are any energy dissipating mechanisms such as friction or turbulence, then heat transfer to the environment occurs. Reversibility requires a direction of heat transfer to reverse for the reverse path. Since dissipative mechanisms cannot be completely eliminated, real processes cannot be reversible. There must be reasons that a real macroscopic processes cannot be reversible. We can imagine them going in reverse. For example, heat transfer occurs spontaneously from hot to cold and never spontaneously in reverse. Furthermore, mechanical energy, such as kinetic energy, can be completely converted to thermal energy by friction, but the reverse is impossible. Yet, it would not violate the first law of thermodynamics for this to happen. In fact, all spontaneous processes, such as bubbles bursting, never go in reverse. There is a second law of thermodynamics law that forbids them from going in reverse. When we study this law, we will learn something about nature and also find that such a law limits the efficiency of heat engines. So for reversible processes, both isothermal and adiabatic processes are reversible in principle. A reversible process is one in which both the system and its environment can return to exactly the states in which they were by following the reverse path. The reverse isothermal and adiabatic paths from B to A and C to A, respectively. Real macroscopic processes are never exactly reversible. In the previous examples of our system is a gas, and its environment is the piston, cylinder, and the rest of the universe. If there are any energy dissipating mechanisms such as friction or turbulence, then heat transfer to the environment occurs for either direction of the piston. So, for example, if the path BA is followed and there is friction, then the gas will be returned to its original state, but the environment will not. It will have been heated in both directions. Reversibility requires the direction of heat transfer to reverse for that reverse path. Since dissipative mechanisms cannot be completely eliminated, real processes cannot be reversible. And this is just the same statement stated down here. So for irreversible processes, the second law of thermodynamics deals with the direction taken by spontaneous processes. Many processes occur spontaneously in one direction only, that is, they are irreversible under a given set of conditions. Although irreversibility is seen in day-to-day life, a broken glass does not resume its original state. For instance, complete irreversibility is a statistical statement that cannot be seen during the lifetime of the universe. More precisely, an irreversible process is one that depends on the path. If the process can go in only one direction, then the reverse path differs fundamentally and the process cannot be reversible. For example, as noted in the previous section, heat involves the transfer of energy from higher to lower temperatures. A cold object in contact with a hot one never gets colder, transferring heat to the hot object and making it hotter. Furthermore, mechanical energy, such as kinetic energy, can be completely converted to thermal energy by friction, but its reverse is impossible. A hot stationary object never spontaneously cools off and starts moving. Yet another example is the expansion of a puff of a gas introduced into one corner of a vacuum chamber. The gas expands to fill the chamber, but it never regroups in the corner. The random motion of the gas molecules could take them all back to the corner, but is never observed to happen. So for here, we have heat going from hot to cold for A. For B, we have the brakes of a car convert its kinetic energy to heat transferred on the environment. The reverse process is impossible. So whenever you hit the brakes in your car, they heat up a little bit, and that's the friction coming from the heat energy. So heat transfer goes into the brakes by friction. So for C, the burst of gas let into this vacuum chamber quickly expands to uniformly fill every part of the chamber. The random motions of the gas molecules will never return them to the corner. So the second law of thermodynamics, the fact that certain processes never occur suggests that there is a law forbidding them to occur. The first law of thermodynamics would allow them to occur. None of these processes violate conservation of energy. The law that forbids these processes is called the second law of thermodynamics. We shall see that the second law can be stated in many ways that may seem different, but which in fact are equivalent. Like all natural laws, the second law of thermodynamics gives insight into nature, and its several statements imply that it is broadly applicable, fundamentally affecting many apparently disparate processes. The already familiar direction of heat transfer from hot to cold is the basis of our first version of the second law of thermodynamics. So the first expression, heat transfer occurs spontaneously from higher to lower temperatures, bodies, but never spontaneously in the reverse direction. So for heat engines, now let us consider a device that uses heat transfer to do work. Such a device is a heat engine. Gasoline and diesel engines, jet engines, and steam turbines are all heat engines that do work by using part of the heat transfer from some source. Heat transfer from the hot object or hot reservoir is denoted by QH, while heat transfer into the cold object or cold reservoir is QC, and the work done by the engine is W. The temperatures of the hot and cold reservoirs are TH and TC respectively. Because a hot reservoir is heated externally, which is energy intensive, it is important that the work is done as efficiently as possible. In fact, we would like W to equal QH and for there to be no heat transfer to the environment, QC equals 0. Unfortunately, this is impossible. The second law of thermodynamics also states, with regard to using heat transfer to do work, it is impossible in any system for heat transfer from a reservoir to completely convert to work in a cyclical process in which the system returns to its initial state. So just like the first part of the second law, it was saying that it is an irreversible process. And we can see that here too. So for A, you have temperature of the hotter object going to temperature of the colder object. So heat transfer occurs spontaneously from hot object to cold one, consistent with the second law. For B, a heat engine represented here by a circle, this is the engine, uses part of the heat transfer to do work. So we see the heat transfer from hot to cold, and we get work out of it. The hot and cold objects are called the hot and cold reservoirs. QH is the heat transfer out of the hot one, W is the work output, and QC is the heat transfer into the cold reservoir. So a cyclical processes brings a system, such as a gas in a cylinder, back to its original state at the end of every cycle. Most heat engines such as reciprocating piston engines and rotating turbines use cyclical processes. The second law states that such engines cannot have perfect conversion of heat transfer into work done. Before going into underlying reasons for the limits on converting heat transfer into work, we need to define the efficiency of a cyclical heat engine. Since a cyclical process brings the system back to its original condition at the end of every cycle, such as a system's internal energy is the same at the beginning and end of every cycle, that is delta U equals 0. The first law states that delta U equals Q minus C, or Q minus W, where Q is heat transfer, but we know that Q here is QH minus QC, and the work is W is being the net work done by the system. Since delta U is equal to 0 for a complete cycle, we now have that W is equal to Q. Thus, the net work done by the system equals the heat transfer into the system. So we substitute Q for QH minus QC. And this is the work done in that process. So the problem is that all processes, there is some heat transfer QC into the environment, and usually a very significant amount of that. In the conversion of energy to work, we're always faced with the problem of getting less out than we put in. We define conversion efficiency, EFF, to be the ratio of useful work output to the energy input, or in other words, the ratio of what we get to what we spend. In that spirit, we define the efficiency of a heat engine to be its net work output W divided by the heat transfer of engine QH. That is, efficiency equals W over QH. So since work is, in this process, QH minus QC, in a cyclical process, we can also express this as QH minus QC over QH. We simplify this, we get 1 minus QC over QH. Making it clear that an efficiency of 1 is 100% is possible only if there is no heat transfer to the environment. So if QC equals 0, then this goes away and our efficiency is 1. That would be 100%. Note that all Q values are positive. The direction of heat transfer is indicated by a plus or minus sign. For example, QC out of the system, and so is preceded by that minus sign. So over here we have 4 steps here. We have our intake. So here is air is mixed with fuel during the intake stroke. For B, we have compression. During the compression stroke, the air-fuel mixture is rapidly compressed in a near adiabatic process as the piston rises with valves closed. Work is done on the gas, so the gas is here. For C, we have power. Our force here is PA. The power stroke has 2 distinct parts. First, the air-fuel mixture is ignited, converting chemical potential energy into thermal energy almost instantaneously, which leads to a great increase in pressure. Then the piston descends and the gas does work by exerting a force through a distance nearly adiabatic process. And D, we have the exhaust. The exhaust stroke expels the hot gas to prepare the engine for another cycle, starting again the intake stroke. So this is a complete cycle right here. So example 15.3, a coal-fired power station is a huge heat engine. It uses heat transfer from burning coal to do work to turn turbines, which are used to generate electricity. In a single day, a large coal power station has 2.5 times 10 to the 14 joules of heat transfer from coal and 1.48 times 10 to the 14 joules of heat transfer into the environment. What is the work done by the power station and what is the efficiency of this? So it is this one for just A and B here. So for A, we have our work done is QH because this is a cyclical process. So we know that we have 2.5 done by the large coal station, and we have QC, which would be the environment here, is 1.48. So we do QH minus QC, and we get 1.02 times 10 to the 14 joules. That is our work done. So for B, we have our work done that we just found over the heat of, or the heat of the turbines, I guess here. That would be 2.5 times 10 to the 14th. So here we see that our efficiency is only at 40.8%. So out of all the work that is done by that the heat transfer of coal, I shouldn't say work, the heat transfer, that'd be your QH by the coal. It's only at 40.8% efficiency. So Carnot's perfect heat engine, we know that from the second law of thermodynamics that a heat engine cannot be 100% efficient, since must always be some heat transfer QC to the environment, which is often called waste heat. How efficient then can a heat engine be? The question was answered at a theoretical level in 1824 by a young French engineer, Sadi Carnot, in his study of a then emerging heat engine technology crucial to the Industrial Revolution. The device, a theoretical cycle, now called the Carnot cycle, which is the most efficient cyclical process possible. The second law of thermodynamics can be restated in terms of the Carnot cycle, and so what Carnot actually discovered was this fundamental law. Any heat engine employing the Carnot cycle is called the Carnot engine. What is crucial to the Carnot cycle, and in fact defines it, is that only reversible processes are used. Irreversible processes involve dissipating factors such as friction and turbulence. This increases heat transfer QC to the environment and reduces the efficiency of the engine. Obviously, then reversible processes are superior. So this states a Carnot engine operating between two given temperatures has a greatest possible efficiency of any heat engine operating between these two temperatures. Furthermore, all engines employing only reversible processes have the same maximum efficiency when operating them between the same given temperatures. So here we have another PV diagram for a Carnot cycle, employing only reversible isothermal and adiabatic processes. Heat transfer QH occurs when into the working substance during the isothermal path AB, between here and here, which takes place at a constant temperature TH, isothermal constant. Heat transfer QC occurs out of the working substance during the isothermal path CD, so from here to here, which takes place at a constant temperature TC. The network output W equals the area inside ABCDA, all right here. Also shown in is a schematic of a Carnot engine operating between hot and cold reservoirs at temperatures T and H. So this one right here. Any heat engine using reversible processes and operating between these two temperatures will have the same maximum efficiency as a Carnot engine. So for here, what Carnot found was that for a perfect heat engine, the ratio QC over QH equals to the ratio of the absolute temperatures of the heat reservoirs. That is, QC over QH equals TC over TH for a Carnot engine. So that the maximum or Carnot efficiency here would be efficiency with the C subscript equals 1 minus TC over TH, and these are given in kelvins. They're absolute temperatures. No real heat engine can do as well as the Carnot efficiency. An actual efficiency of about 0.7 of this maximum is usually the best that can be accomplished. But for the ideal Carnot engine, while a fascinating novelty, has zero power. This makes it unrealistic for any application. Carnot's interesting result implies that 100% efficiency would only be possible only if the absolute temperature of the cold reservoir, T, is 0 Kelvin. That is, only if the cold reservoir were absolute zero, a practical and theoretical impossibility. But the physical implication is that the only way to have all heat transfer go into doing work is to remove all thermal energy, and this requires a cold reservoir at absolute zero, and that's impossible to get to. So here we have 15.25. Real heat engines are less efficient than Carnot engines. That's what's stated in the previous slides. Real engines are irreversible processes, reducing the heat transfer to work. Solid lines represent the actual process. The dashed lines are what Carnot engines would do between the same two reservoirs. So for B, we have friction and other dissipative processes in the output mechanisms of a heat engine convert some of its work output into heat transfer to the environment. So same thing here. For A, we have a schematic diagram showing the heat process, the heat transfer from a cold reservoir to a warm reservoir with a heat pump. The directions of W, QH, and QC are opposite what they would be in a heat engine. So here, the loop is from A to D first instead of A to B. And we see that the temperatures are coming from the cold reservoir to the hot reservoir here. So for the PV diagram for a Carnot cycle, similar to that of figure 15.28, but reversed, following path ADCBA, the area inside the loop is negative, meaning that the network input. There is a heat transfer QC into the system from a cold reservoir along path DC and a heat transfer QH out of the system into a hotter reservoir along BA. So for 2.9, when a real heat engine is run backwards, some of the intent work done, work input W goes into heat transfer before it gets into the heat engine, thereby reducing its performance. In this figure, W prime represents the portion of W that goes into the heat pump, while the remainder of W is lost in the form of frictional heat, QF right here, to the cold reservoir. If all of W had gone into the heat pump, then QH would be greater. The best heat pump uses adiabatic and isothermal processes, since in theory there would be no dissipative processes to reduce the heat transfer to the hot reservoir. So now we're going to go over entropy. There is yet another way of expressing the second law of thermodynamics. This version relates to a concept called entropy. By examining it, we shall see that the directions associated by the second law, heat transfer from hot to cold, for example, are related to the tendency in nature for systems to become disordered and for less energy for less energy to be available for use as work. The entropy of a system can in fact be shown to be a measure of its disorder and its unavailability of energy to do work. The ratio Q over T is defined as the change in entropy, delta S, and is a reversible process. So delta S is Q over T reversed. The SI unit for entropy is joules per Kelvin, because we have heat up here and temperature down here. If temperature changes during the process, then it is usually a good approximation for small changes in temperature to take T to be the average temperature, avoiding the need to use integral calculus to find delta S. The definition of delta S is strictly valid only for reversible processes, such as used in the Carnot engine. However, we can find delta S precisely even for real irreversible processes. The reason is that the entropy S of a system, like internal energy U, depends only on the state of the system and not how it reached that condition. Entropy is a property of state. Thus, the change in the entropy, delta S, of a system between state 1 and state 2 is the same no matter how the change occurs. We just need to find or imagine a reversible process that takes us from state 1 to state 2 and calculate delta S for that process. That will be the change in entropy for any process going from state 1 to state 2. So for figure 15.33, we have state 1 to state 2. Irreversible process has the same delta S. When a system goes from state 1 to state 2, its entropy changes by the same amount delta S, whether a hypothetical reversible path is allowed or a real irreversible path is taken. So for these figures right here, we have A, heat transfer from a hot object to a cold one is an irreversible process that produces an overall increase in entropy. For B, the same final state and thus the same change in entropy, so it doesn't matter if these are diagonal, the heat transfer. So for this example, spontaneous heat transfer from hot to cold is an irreversible process. Calculate the total change in entropy if 4,000 joules of heat transfer occurs from a hot reservoir at TH equals 600 Kelvin to a cold reservoir at 250 Kelvin. assuming that there is no temperature change in either reservoir. Might have gone too far here. Oh, here we go. So for here, we have the change in entropy, right? Delta S. And we can now calculate two changes in entropy. Delta S total is going to be your delta S for H and delta S for C. So for here, we have for the heat transfer from a hot reservoir, remember it's going from hot to cold. So it's leaving that hot reservoir. So this would be negative. So negative 4,000 joules over 600 Kelvin. That would give us negative 6.67 joules per Kelvin. And for the cold reservoir, it is receiving all that energy, or that heat transfer. So this would be positive. And our temperature would be 250. So that'll give us 16 joules per Kelvin. The total change in entropy would be 9.33 joules per Kelvin. So let me see. I think this is pretty similar to that first one right here. So with respect to entropy, there's only two possibilities. Entropy is constant for a reversible process, and it increases for an irreversible process. There is a fourth version of the second law of thermodynamics stated in terms of entropy. The total entropy of a system either increases or remains constant in any process. It never decreases. So for example, heat transfer cannot occur spontaneously from cold to hot because entropy would decrease. Entropy is very different from energy. Entropy is not conserved and increases in all real processes. Entropy is related not only to the unavailability of energy to do work, it is also a measure of disorder. This notion was initially postulated by Ludwig Boltzmann in the 1800s. For example, melting a block of ice means taking a highly structured and orderly system of water molecules and converting it into a disorderly liquid in which molecules have no fixed positions. There is a large increase in entropy in that process. In another easily imagined for example, suppose we mix equal masses of water originally at two different temperatures, say 20 and 40 C. The result is water at intermediate temperature 30. Three outcomes have resulted. Entropy has increased, some energy has become unavailable to do work, and the system has become less orderly. Let us think about each of these three results. First, entropy has increased because mixing the two bodies of water has the same effect as heat transfer from the hot one and the same heat transfer into the cold one. The mixing decreases the entropy of the hot water, but increases the entropy of the cold water by the greater amount, producing an overall increase in entropy. Second, once the two masses of water are increased, there is only one temperature. You cannot run a heat engine with them. The energy that could have been used to run a heat engine is unavailable to do work now. Third, the mixture is less orderly, or to use another term, less structured, rather than having two masses at different temperatures and with different distributions of molecular speeds. We now have a single mass with a uniform temperature. These three results, entropy, unavailability of energy, and disorder, are not only related but are in fact essentially equivalent. So for this example, when ice melts, it becomes more disorderly and less structured. See the molecules here? It goes from this ice to water where it can be just kind of free and roaming around. So that would do it for chapter 15. As I mentioned, this is a big topic when it comes to physics. So I would definitely, dive into this chapter, learn a lot about it, go over the different definitions of it, the different laws, the different versions of the second law, and the equations are pretty much consistent throughout. You can use them for a lot of these topics here, like del to U equals Q minus W. That's consistent throughout the whole chapter. So definitely look over these.